Hello, my friends. Hello, my RF and microwave design engineers. My name is Dr. Mohamed Nezami, and welcome to another one of my lectures. I'm continuing my series on the topic of microstrip line to substrate integrated waveguide transition with tapered matching, tapered line that will match between a microstrip line and a substrate integrated waveguide. We insert a little tapered microstrip line that will basically do the matching between them. Now, like I said, now in my the first part, which is this one here, it's online already in this playlist, Substrate Integrated Waveguide Circuits. I covered some of the basics, principles of the Substrate Integrated Waveguide, but today we're gonna move on further, okay? I operate out of Jerash, Jordan. That's the city behind me back there. That's the little town, ancient Roman town. I work as a freelance RF and microwave designer. My rate is very reasonable. You can reach me at this number here via either phone call or via some of the apps, the Android apps or iPhone apps like Telegram, WhatsApp. Okay. Meanwhile, also my email is this here, Mohamed_Nizami@msn.com. Okay, so ladies and gentlemen, let's start now let's continue with what I was doing last time. Okay, as you know, last time we introduced the concept where we have a substrate integrated waveguide that is here in this case. Okay. Although I forgot to put some vias in here. I borrowed this figure from the open publication. We should have vias on each side, okay? And we have a 50 ohm line in here with a width that is W. And the microstrip line, as you know, operates in the quasi-TEM mode, as you most of you are aware of. And then the waveguide itself, the substrate integrated waveguide, is a pure TE propagation mode, okay? And like you see here in the E-field distribution, what we want to do, we want transparently transfer all of the signal that comes in through this line onto the another media, which is a waveguide, planar waveguide, and that has a propagation mode that is completely TE without losing any of the energy in the transition here, region in here, as you can see in here, okay? So the idea is that we introduce this, and then today we're going to introduce the tapered line principles, okay? Tapered microstrip line matching concept, where if we are faced with to go from a microstrip to another load, 50 ohm to another load, where we can use tapered line to transform the impedance and do full match with maximum return loss. Okay, so last time we also showed in this figure, basically what we have to do is we get the substrate integrated waveguide, as you can see here. This is copper. And so all we need to do, we need to insert this tapered line in here. And this tapered line, there are design rules that we have to follow in order to achieve the best performance of transferring the most all of the energy in here from the microstrip line to the TE10 mode substrate integrated waveguide with minimal losses. Okay, and that involves basically is three regions where we have to match, where we have an impedance of Z1, say, or the feed line in here, which could be 50 ohm most times. Okay, and then we have the Z substrate integrated waveguide that we were able to calculate from the part one of the series using the either closed formulas or from the HFSS 3D analysis, okay? And then what we have to do, we have to transform, somehow put in the middle a match. These ZSIWs usually their low impedances. They're like somewhere between, I would say, 25 ohm down to 15 ohm, depending on the structure of this waveguide. And then we got 50 ohm. Okay, so we go from 50 to smaller impedance, and we have to match it that way. So we have to match using this section in here, and that's the concept, that's the topic of this session, okay, is how do we design a taper line, which basically involves figuring out the length, which we said last time, it's got to be a quarter wavelength or multiple odd numbers of a quarter wavelength. And then the width in here, this width in here, is computed based on principles that we're going to demonstrate, okay? So let's just talk in general right now about the tapered line impedance matching, okay? And tapered line impedance matching, you can find those in a lot of applications, not just matching to between a microstrip line to substrate integrated waveguide, but you can find them also from microstrip line to microstrip line, where we, for instance, in here, look at this. This is a switch, a broadband switch. And of course, when you're talking broadband switch, these are the switches that right now are available. A lot of them are in the, they operate from DC to like 50 gigahertz or so. And impedance, the input impedance could be very high in here, okay? And then what we need to do, we need to come in from 50 ohm to this high impedance in here. And therefore, we can use a tapered line transformer to do that matching. Another application we've seen utilized is in the Dorothy power amplifier, the Dorothy power amplifier, okay, gas or the other technologies. And so we have it in here, and this tapered line in here is using the Klopfenstein taper, which is one of the things that we're going to cover today. Okay, it's just one mathematically one form of mathematics that describes the gradual transition from this low impedance point in here to this 50 ohm in here. Okay, so conceptually, the tapered line transformation or matching between two impedances, say between Z0 in here and R load, we need to go from here to this here. We can either use uniform length quarter wave transformer to get from this impedance to this impedance over this length in here, or we could use a smooth transition. And that smooth transition in here, as we will see in a moment, has several ways to get here. What we can do, depending on how fast is the roll off of coming down or going up between the two impedances, that can be described as a smooth transition using one of the conventional tapered lines that we will describe in a moment. And this usually follows either exponential, linear, or triangular, or Klopfenstein, okay? Or we could use it, utilize a step transformer just like we see here, okay? Or we could, if you want, go just one shot, one step jump in the impedance. So we could be coming here and then jumping all the way in the middle here, jumping to the next one, okay? So here are the classes of tapered lines. And so this here describes how the taper line transition between two impedances, Z1 and Z2, which are basically how to go from this impedance to this impedance. Mathematically, that's the shape of that we can follow here for this one here. This can be either exponentially transition or triangular or Klopfenstein, okay? And the Klopfenstein is a taper line, a special one, and that is commonly used for broadband impedances matching. And it was really first described in 1956 by Klopfenstein, and you can refer to this paper. It's available online, okay? And then we've got two other curved mathematical representation of of this transition in here that I've rarely seen this used. I usually see exponential or Klopfenstein. Okay, now it turns out, now you can go to the publications and see this published. There's a lot of publications, and also there's I'm going to show you in a minute. David Bozar described this really well on page 250, where we'll go there and see in a minute, okay? And so the exponential one is basically this. So you start from the Z1 on this side here, and then you climb up parabolically to exponentially using this term in here as a function of the length. So if you look at, it turns out that if you look at it now, depending on which one would you use? So that's the question. Do you use exponential, triangular, Klopfenstein, or any of the other ones? It turns out the answer is really here. Now, a lot of times we jump on one of these, exponential or linear or Klopfenstein, and just do it. But really the justification for this is the fact that if you sweep the input the input from here to here as a function of one of these topologies, it turns out that if you look closely at the return loss, okay, as a function of the electrical length in here or physical length, okay, you can see that if your line is short, say up to 10 degrees in here, BL is 10, you can see that, or even less, like say 7, you can see that the exponential one has the lowest return loss, okay? And then now, if you look at all of the other ones, if you're really relatively long, if the line is relatively long, then obviously you need to, the exponential one has higher return loss, lower return loss. So you need to go to higher return loss, which means you could choose, for instance, the cosine or the green one in here, which is the Klopfenstein. And that's, if you look at the green one, really, that's probably why this transformer is widely used for long lines, okay, for broadband impedance matching. So that's what it is. So now what I'm going to do today is what I did is I used ADS to do some analysis of examples, just showing you what we have in terms of the of basically the trade-offs between all these classes that we have here. So we'll go to that in a moment. So let's start with the simplest one, which is multi-section quarter wavelength impedance matching. So again, what we're trying to do, why we're doing this, is because we need to get to the point where we can derive the taper, which is the taper length and the taper width on here, of the impedance matching between a microstrip line and a substrate integrated waveguide. Okay, so that's really what we need to do. So what I'm doing today here is I'm describing basically this taper in here, the trade-offs between various classes of taper. So you don't have like I said in the beginning, we don't have to go smooth. So we could go to this one here, which is basically this technique in here where we do steps, equal steps, to get from between Z1 and Z2. And that is because we want to get from this impedance of the 50 ohm line, for instance, here, to the SIW in here. So to get to this, we could do this one here, which is pretty simple to draw. As you know, you need to draw this for BCBs and analyze it. So you either have to do it in HFSS or some other package. And if you want to do a smooth taper like these, you have to draw mathematically. And a lot of engineers find it difficult to implement this in HFSS, although it's not really that hard. Where the step one can give you a comparable performance, and it's pretty simple to implement, okay? So if you're trying to do multi-step quarter wave transformation between two impedances, which is the blue line in here, we have two choices. We can go either binomial or Chebyshev, okay? Now, in Beaux-Arts, he covered this really. Let's go to page 240, I think. Okay, I think we start here, where, yeah, here, the quarter wave transformer, okay? And we go down and he describes all of the aspects of this. Even he gives you the tables for Chebyshev and the binomial, oh no, the other one. Okay, so and he gives you some examples and so forth, and he covers also the okay, here's the Chebyshev. That was the other. What was the other one? That was the binomial. I'm sorry, the binomial. Okay, so basically, and then he goes into the table line in here. Okay, and that's where he covers the Klopfenstein, basically his Klopfenstein table, and he does that principally. He derives all of that. So if you need to understand the principles of that, you know, you can go to his book. Okay, so let's get back to here. So the multi-section quarter wavelength design is really simple. Okay, you've got they give you these tables, whether you want to go Chebyshev or binomial. You have to, the first thing you have to determine what is the like, for instance, let's talk about this example in here. So I have a 100 ohm resistor, a 100 ohm load, and I have a 50 ohm source at 10 gigahertz. And what I want to do is I want to match using a 4 sections of a transmission line. In this case, I forgot what I did here, but we'll go in a minute. So what you need to do for Chebyshev and binomial, it's very similar. The first thing you determine what is the order, okay? And then what is the ratio of the Z load to ZG? Okay, let me magnify this. So we have the load to characteristic impedance that you're trying to operate at, which is this piece here. So here's the source, small section, and here's a load. And in this case, I'm matching using 3 sections. These are 3 sections. So if you go, so for instance, if the load, say 100 ohm, like in, well, let's just go to the example. Sorry, here it is. Okay. So what I'm trying to do is I'm gonna match between two impedances, okay? In this case, 100 ohm and 50 ohm, okay? So I've got an extension of the 100 ohm in here, an extension of the 50 ohm in here, and I've got, this is 4 sections, okay, of this here, okay, which in this case, it's for using the binomial transformer, okay? So I want to do binomial transformer, 4 sections, matching, inner matching between 100 and 50 ohms. The ratio 150 ohm, of course, is 2. So you come in here, Z load over ZO, which is 2, and then you go to the section that has 40, which, and then in this case, you give you the first section, the first quarter wave section, the impedance Z1 is really 1.04 times ZO. And that's understandable. So we start, because it's tapered, so we have to start very close to 50 ohm, okay? And then we have to finish close to 100 ohm, and that's 1.9, which means Z4 over ZO is equal almost to, which is 100 ohm, okay? And that's basically what we have here. So you have these impedances, you calculate basically all these impedances, okay, all these ratios, and then you come up with these impedances. So it turns out that the impedances is 52 ohm. First you start with 50, that's your source. You got 52 ohm, then 62, 80, and 95. And then you've got a section 100, and then the load is 100. So using ideal transmission line in here, okay, we can actually, so again, what we have, we're trying to match the 100 ohm to 50 ohm using a 4 section quarter wave line sections using the binomial transformer topology, okay? And what we did is we went to the tables, okay? These tables are tabulated and people publish these tables. You can find them in the Bozar book and some other books as well. So first of all, we figured we need 4 sections, okay? And that's based on the bandwidth requirements, okay? So we've got 4 sections, and the impedance ratio between the load to the source is 2, because we've got Z load over ZO, which is 100 over 50, which is 2, and we go to 4 sections. So we have the 4 normalized impedances of the 4 sections of a quarter wave transformers. Okay, so we've got, and so the first thing I did is I put this on the ADS using ideal transmission lines just to verify. So we've got the 4 sections, okay? Each one of these is 90 degree at 10 gigahertz, okay? And then I put the impedances. I calculated the impedances based on this here, based on these entries in this table, okay? And I put them in here, okay? And then I simulate it, and that's what I get. So it works perfect, it looks good, everything is fine. So we did verify this. Now, the next step, you have to implement this using microstrip line. Or let's do first of all. So we've got these. These are this one's here. So what we would do is we wanna, if you want to simulate this, you just go like this, and basically this is what you have. So okay, so get a marker somewhere in there, and that's what we get. Of course, this is using ideal 4-section transmission lines, okay? So the next thing what we want to do is we want to transform this to microstrip lines, okay? So what I do is I have a substrate, which is this substrate in here, and this substrate is a duroid, 2.2 half millimeter height, okay? So what we will do is we want to implement all of this in microstrip, and that's basically now. So what I do is I go to ADS, okay? So let me open the other file that has this. Okay, so I went in and put the substrate. Here's the substrate that I need, and this is what we have. This is what we have here, and we need to get these impedances 52, 62, 80, 95 into a microstrip lines. And so what I need to do is we go to tools in here, and we run the line calc. We start line calc, and of course we come in here. For instance, let's say that I want to implement the 95 ohms. So here's 95, okay, and of course 90 degrees, and using these the parameter substrate at the frequency of 10 gigahertz, and then I hit analyze and or synthesize, and basically here it is, a half millimeter, and that's what I got basically here, as you can see. So I grab this line here, and then I put it in here, and of course the length in millimeters is also this. And you go one by one and do this on all of them, okay? So I did this, and at the same time, what I did is I put a section which transforms 100 ohm to 50 ohm using a single order transmission line, okay? Quarter wavelength line. So a single transformer now versus 4 orders. And then when I run this, okay, basically this is what I get. So you can see here that this is, let's zoom in a little bit here. And let's go here, 0. And let's go here, let's say 2. So we can see really close in on the insertion loss. And you can see this is what we get. So we've got the single line, the single transformer is this here. Okay, I've got the 4 section transformation is here. It's pretty good, very wide bandwidth. And the theoretical ideal one is here. Okay, so this works very well. So, and then of course, you can show the layout of this. So go layout in here, and then got the layouts here. So here's one section, and here's the 4 sections of the transformer in here. This is the little 100 ohm, and this is a 50 ohm extension. Okay. So this is basically, if you were to design this using a binomial transformer method, okay? Next, what we want to do, so we did this, of course, here. Let's say another example, just to show the Chebyshev, okay? So Chebyshev is, we do exactly the same, except we go back to these tables, we turn to the Chebyshev, and the Chebyshev, as opposed to the binomial, there's an additional parameter that we have to specify. Now, if you want to know how these table numbers, we got them, of course, they're explained in filter synthesis books like the Matthews or some other books, and you can see those. So what we have to specify in here is the maximum reflection coefficient, okay, in addition to the Z load over Z naught and the order, okay? And so in the example in here that I have here, so I have 100 ohm source, load, to 50 ohm load, and what I want to do, three sections using Chebyshev transformers, okay? So it's a third order. So if you do that, so we come back, we go to this table, we have N3, and then we have 0.05. 0.05 is the, 0.15, which is about minus 16 dB of return loss. So we've got 0.15, and we don't have 0.15, but we have 0.2, which will work fine. Okay, so what we will do is we're going to go thread section, and of course 2 is the Z load over Z naught here, and you got these three numbers in here. So we're going to grab these three numbers in here, okay? And so the first impedance is 1.14, and the second impedance is 1.4, and the third impedance is 1.74. And these impedances, it turns out, that's here, I have them right here, okay? And so the value of these impedances is 57, 70.7, and 87. So you go to link calc, and one by one, you can actually synthesize these lines in the substrate that I'm using, which is a DK 2.2 and height of 0.508. And this is what I got, okay? And let's go and see that. So we're going to go to this one here, hopefully. Yeah, here it is. So we've got three sections, okay? The impedances are given all in here, same substrate, and I still have the single order. Synthesize that, and boom. So what I do is I have, here's a single order. Here's a single order one, okay? And here's the third order one, both the insertion loss and the return loss. So let's look here. And you can see that here, okay? All right, so that's what we have. So on the using, so of course you do the layout for this, and just to see what it looks like. This is what it looks like, okay? And this is the single section, of course. Okay, so let's go further. Next, okay, so this is just a comparison of the fourth order and the third order. You can see the comparison in here. Okay, so let's see if I did that here, if I still have that file. So we can come to here, and okay, so what I have is I have the ideal one, and then the first one, fourth order, and the third order. This is Chebyshev, this is binomial. And let's do the simulation. We did that. Okay, you can see the comparison of those here, and you can see the insertion loss as well. This is a single order, and these are both of them. So very similar. Okay. And the layout is, of course, you know how to get that. So let's save time and move on. Okay. Oh, okay. So now next, what I want to do is, okay, so we know how to do it manually now. So the way to do multi-section quarter wave step transformer design is based on these tables, okay? The tabulations for binomial multi-section matching transformer and the Chebyshev for multi-section matching transformer. So all we need to do is get the order, and then get the Z load over Z naught, and then look up the terms, and that's your impedances, and then you go to a Microstrip synthesizer program, link calc or something else, and then synthesize all these lines to your particular substrate. So, but look, computer aided tools are available. So why don't we just then use ADS? Well, ADS turns out that it does have a library of table line sections, and let's just show you how you do that. The first one I want to do is to look back in the on these lines on this line here, on this table transmission line. In a lot of cases, practicing engineers don't have time to do like a thesis out of this. This could be a job that you have to turn in like in an hour or in minutes sometimes. So you got your 50 ohm line in your substrate, and you've got the SIW, and numerically you calculate what that line should be. Okay, so what you could do is you could just, or you can find the impedance of this substrate integrated waveguide. So you could use just a single order linear transformation, and that may work very well for you in a lot of cases. So to do that, you know, ADS has got this symbol, which is mTable, okay? And all that is basically is a transformer, which is that first one in that table here. Let's see the linear one. We didn't describe the linear one in here. Sorry. But it's a linear transformer that transformed impedance where when the length is 0, okay, and that's 0 here, basically the input impedance is Z2, okay, and then when the length is equal L at the end of the line, and here the impedance is Z2, Z1 versus Z2. And this works out well. So what I'm going to do here, for instance, let's say that I have 50 ohm to 10 ohms, okay? And that's what I'm going to do is I put in this line in here, and this is available in ADS. Okay, so let's look in here. So what I do is you go in here to the microstrip line in here. Let's see, where you go, microstrip. Okay, so we're going to go to Microstrip. You can pick a table line out of this right here, like this example in here, and then you can actually do this. So actually, that's a smart one. It's the other one is in the other directory, but in any case. So and when you look at this, all you need to do for this is specify the width 1, the width 2, and the length. Okay, and that is basically, if you look at the help file on this, it gives you all these parameters that you need to specify. So it's pretty simple. If you have, you know, your width already on the microstrip line, on the other side or in here, and then you need the other load, which is a lower impedance. So all you need to do is specify these 3 parameters, and you got yourself going. And that's basically what I did here as an example. I have a 50 ohm, which is width 1 in this case here, okay, and I have a width 2, which is 11 millimeter, okay. And what I want to do is I want to do the matching between these two, and you can run these and find out actually like this. So okay. And if you look at the layout of this is like this. So that's basically you know, doable. So you can go to layout, and here it is. So basically what you could do is you could just basically copy this into your schematic capture into your BCB, and you're done. Okay, so that's one way to do this. Okay, so now, like I said earlier, that we can do the multi-sections quarter wavelength computation of the impedance is required. We can design it using tables available, which are available in this case in Posar's book. So you can go to Posar's book, and they have these tables. But what we can do, ADS also gives us actually this component in here, which is a smart component. And you can use design guide, okay, to design this quarter wave transformer multisection. And all you have to do is you come in here and you specify the frequency, you give it the bandwidth, fractional bandwidth, and you give it the load and source and the number of sections, and then the topology, whether it's Chebyshev, uniform, or binomial, okay? They even got one additional section choice, which is uniform. In Beaux-Arts book, we only have binomial and Chebyshev, okay? So, and then you can actually design that. And that's what I'm going to show next is, so let's take an example. So I've got a load, which is 10 ohm. I've got a source, which is 50 ohm. And I want at 10 gigahertz to use 7 sections of a quarter wavelength line and design it. And this is the here. This section is available in the design guide components in here. So you go to passive circuits, design guide, microstrip circuits, and we have it right here. So you can there it is right here. So you can use this. And again, I give you what the specifications are. So let's do this. Let's run this, and there you go. So I've got this is a response, okay, which is very nice, broadband, all the way from 3 gig to 15 gig, 7 sections. Now, what you can do is you can look underneath what this was. What it turns out is you design, and here it is. It gives you even from input to output, all the lines, all the sections, including the step discontinuity modeled in there, okay? And of course, you can also look at the layout, generate the layout for this. And there it is, okay? So what I've got is I put a ruler in here, which is 36 millimeter. So you got 1 section, 2 section, 3, 4, 5, 6, 7. Here's 7 lines, okay? So that's pretty good then. So that really, so anytime you have a design, you can you know, do it this way, where you can do this, or you can do the other one. The other ones, which is basically to go back and do it manual, okay? So let's get back to this again now. Let me show you one thing. So we have this one here, of course, right now is specified for Chebyshev, okay? But what you can do is you can go in, and this field in here gives you a choice of doing it the other way. So you can do binomial or uniform, okay? And so let's see what I did next. Is, okay, let's do a Klopfenstein. So now let's go to a table, smooth transition table topologies. And those are basically, according to the table that I have here, are basically exponential, triangular, or Klopfenstein. So we're going to look at these three types, which are here. As you can see now, of course, like I said before, depending on the electrical length between the source and load that you're trying to match, the transformer, you can actually make a choice, a smarter choice of which topology to go, Klopfenstein or exponential or triangular. Okay, I'm not going to pay attention to the other two, just because, as you can see, the return loss is not really good on the other ones, but they're mentioned in this, where I grabbed this from the IEEE publications. So again, let's do one design. So basically, Klopfenstein is again, ADS gave us, basically, they gave us a way to design with this. So we're going to go to that example. So here it is. So we have a TL match, okay? And if you click on this, here are the parameters. And in this field, you can do Klopfenstein, or you can do exponential or triangular, as you can see in here. So what I'm going to do for this one here is so again, we've got 10 ohm, got 50, we've got a load of 10 ohm and 50. Oh, by the way, I forgot to mention one thing. When you go to this table, these here, do it if you're trying to do this manually. As you can see in here, the Z load over ZO is always, in this case, these tables are for greater than 1 ratio. What if you have the load, okay, is lower than the characteristic impedance? So these numbers become less than 1. Well, it turns out you do the same thing, except you reverse it, okay? So make it 1 over that, and then just reverse the order of the lines in here, okay? So just, it's good that I didn't forget that. Okay, so we're gonna do Klopfenstein between 10 ohm and 50 ohm. And that's what we have here. So what I did at 10 gigahertz, okay? And if you simulate this, here it is basically. Pretty good, and everything is fine. Now the layout, what if you want to look underneath this, what it is, it's basically here it is. Now in this case in here, by the way, I specified the order of this, which is 4, a low order, okay? Just so that for the specific bandwidth that I'm trying to do, that was sufficient. And these are the lines that you can see, okay, in here. And you can see the width with 1 to 2, how it transitioned between all of them, okay? And if you look at the layout of this, of course, is an interesting layout, and here it is, okay? Now, when you're trying to, if you're trying to include this into your 3D EM modeling, if you don't want to do it in pathways, you want to transform this either to HFSS or CST. You could either transform, export this as Gerber file or DXF and then import it over there, or you can just draw it mathematically. And to draw this mathematically, HFSS has a method of drawing this function mathematically, okay? So I'm not aware of HFSS whether they have a library for these transformers or not, but this is doable. Okay, so let's go then try the exponential one. Okay, so what we did is we went in, same circuit, except what I'm going to do now is choose exponential, and that's this here. Same thing again, if you run it, basically, this is what you get. It's pretty good, a little different, of course. And then if you look at the layout, it's also different for this because this is exponential. Now you can see, there you go, you can see the shape of exponential in here. On this side, it's positive parabola, and this one is the negative parabola, and along the x-axis. Okay, so now again, like I said, this has a few choices that you can do. So we can go try triangular, and then we're going to compare all of them together. So we did a triangular one. Okay, well, let's look at this without even just showing. Okay, so here's a triangular one. Triangular one is interesting because you divide the length of the transformer into 2 sections, from 0 to L over 2 to the middle, and then from the middle to the full length. And each one of those is described different. You can see that in the slope in here, in the exponential slope. But it works the same thing, okay? So here's a diagram showing all 3 of them. And here's also the layout. And you can see that there is a trade-off between the orders, although I may have given them different orders in this case. Let's see, this is 4, this is 4, and this is 4. Actually, it's the same order. So there is definitely, they're all for the same order, except now you can see that the lengths are different. Okay, exponentially is the longest one. Okay. All right, so so with this now, let's see, where did I do the comparison? Okay, so what I did is I put all of 3 together in here, and if we run them all, that's what you get. So you get close in. This was designed for 10 gigahertz, of course, and you can see that the resonance in here is around 10 somewhere. So you can see that you know, there is definitely a trade-off between them. Now, with this, now let's get back to what we started talking about. I mean, we are not really, the concept was is that we really want to do SIW to microstrip line transition But we ventured off and did a little exploration of this the table line design. Okay, so there are different ways to do the gradual transformation of the impedance between the characteristic impedance of the input line and the waveguide, the SIW, between them, and that way we're aware of different trade-off sections that we can do, namely the what I just showed, where we started out. We can see that we can either go with a stepped transformer, okay, or with smooth transition, okay. And the smooth transition, there are a few cases where a few things to consider. We can go exponential or triangular or Klopfenstein, okay. And these ones, of course, depending on the length that we want to do the transformer, basically there are some trade-offs. The multi-section quarter wavelength transformers, it's very easy to design. You can go to the tables, whether it's binomial or Chebyshev, and you, depending on the order. Now, the order, there are ways to derive the number of the orders, but as a practicing engineer, you can just go in and start adding or increasing the order until you get with your simulator, you're satisfied with the bandwidth requirements. Or you can go to the equations and figure out, depending on the bandwidth, the starting frequency, the ending frequency, and you can actually find out how many sections do you need to fulfill these requirements that you have. Okay, so you pick the order. In the binomial case, you pick the order, and then depending on the load to characteristic impedance on the input ratio, you find the entries where you are, and then figure out what the impedances are, and then you synthesize those in Microstrip. Same thing you do with the Chebyshev. So, and then we said, okay, let's go to basically we can do that from tables, or we can do that using the ADS smart thing. So you can see, this one is where we grabbed it, is from here. It's from the design guide, Microstrip circuits in the ADS, and that's here. Okay, so that's this. And when you design this, you basically just go like this, and you go to the design guide, and then passive circuits. And in here, actually, they give you a controller to do the design and even simulate. So in this case, we can design it. It was designed, and it can simulate even. So we can do this, and it can simulate it for you. And you can work offline, actually trying to do that as well. So, okay. So, and then we did that. We looked at the Klopfenstein transformer versus the exponential and triangular transition, and so it's up to the designer. Okay, so this is all I have in this session. So I hope you have some clear picture now on the table line impedance matching between two sections, and our target, of course, we're trying to zoom in on the substrate integrated waveguide to microstrip line transition. So the third part is, I'm going to go back and let's just zoom in on this and do one, okay, and model it in 3D and see the trade-offs where we can actually going to be optimizing the length and width of this table, okay, and starting out from this here, we're going to start out with a solution in closed form, and then take it into HFSS and see what happened next, okay? So again, this is Dr. Mohamed Nezami, thanking you for your time. Please go to my channel, and please, if you could, this is my channel, these are my videos. And if you go to, I've got a lot of these videos. I hope you find them interesting. Please do subscribe. I would appreciate if you subscribe, and check out my playlist. In the playlist, of course, you're going to find out one which is basically substrate integrated waveguides, and that's basically you're going to get a list of these videos in here. Okay, among them is the first part, and then this very same video that I'm doing right now is going to be in minutes, it's going to be uploaded there. Okay, so again, if you happen to have any opportunity to do co-work with you on any project, my rate is very inexpensive. I operate out of Jordan, much cheaper than the United States and Europe. I have clients, proven relationship with clients in the US, Europe, India, Malaysia, Singapore, Saudi Arabia. I would appreciate if you give me a call. Consultation is free up to 5 hours. Okay. I take your design from concept all the way to fab files. So I work with you on the fabrication, on the BC board. I work with you on component selection, bill of material. I take from concept to system simulation, and then to BCB. Okay, I work with you also with if you want to assemble this in China, and even give you options if you don't want to use. If you have some difficulty getting parts from the United States, we can actually shift the design to utilize Korean and Chinese parts. So you can do the full assembly in China, and then I work with you during the testing as well. Okay, so until I see you next time, please have a great time, and thank you for watching. Have a good day.